This week we're going to make a liquid-liquid phase diagram, and we're going to do this with two liquids that are immiscible or will not mix at low temperature and miscible at high temperature. Now, the amount of chemical present makes a difference in when they become miscible. And so we're going to do an experiment which will allow us to make a phase diagram. And so the phase diagram that we're going to make today is a two-dimensional map that describes the condition of our system. And so we're going to look at the relationship of temperature to amount present for our phase diagram. We could do other variables that include pressure or composition and those types of things. Now, why would we want to be able to make one of these or utilize it? Well, they're actually very useful for designing process routes or predicting properties of compounds and mixtures. And I'll show a nice example or two of that as we look forward. Most ceramic engineering or material science programs have courses entirely devoted to phase diagrams. Here's a couple common ones. This is a one-component phase diagram, and what it's showing is this one is for water, and there's some points that you would recognize on here. At 1 atmosphere, 760 millimeters of mercury, if we trace this over to what we would call the fusion line, then the line between ice and liquid, then what we would find is that if we go down to the temperature line, so a pressure of 1 atmosphere and a temperature of 0, we have the freezing point of water. And so if we follow that line on over, and now we're at the vaporization line, and if we look at that, then we're at 100 degrees, which that's the boiling point of water. If we lower the pressure, then the boiling point of water diminishes. If we increase the pressure, then it actually increases that temperature. That's why pressure cookers cook faster, or if we lower the pressure when we go into the mountains, it takes longer for our pasta to boil because we no longer have 1 atmosphere of pressure. And so those changes that, well, they're described by the phase diagram, and so we can follow that out. There's an interesting point here. It's called the triple point, and that's where all three phases coexist. And so where we have gas, liquid, and water all together. Now, we often see another thing going across right here. This line defines where sublimation occurs, and so we have solid going directly to vapor. Happens in a freezer, for example. That's why your ice over time becomes less dense as it leaves in that process of sublimation. This is a carbon phase diagram, and it's actually showing you where the diamond region is a liquid region and the graphitic region based on temperature and pressure. And so that shows carbon and would be useful to find the conditions to make diamonds, for example, for abrasive saws, bits. You can actually get these more detailed, and we can add in other components. And so this is showing a phase diagram that it still includes carbon, but we also put in 2 other elements, and as you can see, they get much more complex. Now, we're not going to have to do anything this complex for today's lab, but just letting you see an example which shows the isothermal lines and the compounds that form in those regions on those isotherms. So, all right. So, we've already been talking about some of these points. Their phase diagram is a visual representation of phase changes, and triple point is where in a single component is where all 3 phases exist and curves branching out. So if I look at those curves, then we're seeing those. Just a reminder one more time, this is the fusion line, vaporization line, and sublimation line. And so in those regions, we can talk about each of those. Ultimately, as we cover these in class, then I'll expect you guys to utilize a phase diagram to make some predictions and understand and name the different lines and those types of things. All right. So this is an argument for why they're important. And so you guys can read through these as you're working forward. But I'm going to show you an example which I think clearly shows an important situation in the real world. Every fall, we're in the fall right now, as the opportunity for a freeze to occur, we should check our radiators to make sure that there's the appropriate amount of antifreeze in them. And so this is actually showing an ethylene glycol percent with water, and so a mixture. And what it shows is that if I have 100% ethylene glycol, the freezing point in Fahrenheit, I'll use that for today just to let you know, is right around 10 degrees. But if I go over and I look at pure water, I find that it's at 32 degrees Fahrenheit. And so you can see this is when I'm 100% water, this is when I'm 100% ethylene glycol. But as I start to add ethylene glycol to my water, what I notice, this curved line coming down, is the freezing point of the mixture. And so when I get up to about 55%, then, well, I reach the experimental limitations. But what I can see is that, well, let's think about the state of Missouri. If I'm in Missouri, well, negative 18 is probably colder than it's going to get at any time. And so if I come out, then that means if I have a ratio that's somewhere between 44% and about 80%, then I would cover that negative 18. Now, if I lived in Barrow, Alaska, I would definitely want to get up and to about 60 to 70% ethylene glycol in my mixture to get that lowest freezing point. And so this is a useful phase diagram and explains a lot that I didn't know when I was in my youth and thought I should use 100% ethylene glycol because it had to be better. The stronger the better, right? And so that's a misnomer in the chemistry world. All right, so our experiment today, we're going to make a phase diagram with a different system. We're actually going to use water and 2,4-pentadione, and I'll often refer to it as acetylacetone. The 2,4-pentadione has a common name, which I learned in my younger days. But now what I should know is that they're not miscible at room temperature. So when I put them together, the acetylacetone is less dense, it sits on top, and so I have two phases. But when I start to heat it, then they will mix, okay? Once I get them mixed, then I'm going to let them cool down with the thermometer in them. And when I see cloudiness, then I'm going to record the temperature to the nearest tenth of a degree. And so we're going to do multiple ratios, enough that we can get a nice plot, and we'll be able to look at that. Now, it's an interesting relationship, much like the ethylene glycol phase diagram. This is going to be a non-linear curve when I go to plot the data. So we'll talk about that as I show you how to graph that on Friday. All right. I think I've covered this on that last slide in terms of you're going to have a hot water bath. You're going to heat up your test tube with your mixture in it. You're going to have a thermometer in it. Once it starts to cool, and watch for cloudiness, and you should be able to make those observations, get XY data points, and be able to plot that temperature and volume fraction. So anyway, how do I calculate the volume fraction? Basically, it's going to be the volume of 2,4-pentadione that you put in your test tube plus the total volume, the volume of the 2,4-pentadione plus the volume of the water. And you should have a number of different fractions that you look at in that relationship. You're going to do this delivery with a burette, so be sure and record your volume initial and your volume final so you can find the volume that you delivered into each test tube. All right, that's Bert. And Bert is geared up to deal with some form of concentrated acid. He has his face mask on, his goggles, his apron, lab coat, impermeable gloves, and he actually has his acid in secondary containment as he moves it. And so that's appropriate safety for what he's working with. Now, for today, we need to talk about what we need to be safe to do today. And organic substances can't be put down the drain, so we have a container in the back for this. We're going to put all the 2,4-pentadione and water mixture into the label container under the hood. And We're going to wash our hands when we get done. We're going to handle the 2,4-pentadione in the hood. We'll have your burettes set up in the hood to deliver with. Only when you have them out on the bench and are heating them should you take the stopper out of them, and then be sure and keep your safety glasses on for the experiment. That's all I have for today. Well, that's our first discussion on phase diagrams. I'll talk about the graphing in class, and so see you in lab.